Welcome. In this video I want to focus on the definition of continuity. So I'll start with the definition that we have in the notes in the text, which is in terms of a sequence. And so we sometimes call this the sequential definition of continuity. But towards the end we'll see a theorem that this is equivalent to an epsilon delta condition. Sometimes the epsilon delta is given as the definition and then the sequence is shown to be equivalent, but this is the order that we're taking. The sequence definition can be more useful abstractly, but if you want to show that a particular function is continuous, then often the epsilon delta is what makes sense. So the definition that we have at hand, I'm breaking it here into three parts. First of all, fundamentally, we're talking about continuity at a particular point. And so this is to say that if you have any sequence, we say that the sequence must be in the domain of the function so that everything is going to make sense. But for any sequence converging to that point A, we have to have the resulting sequence, once we apply the function f, converging to f of A. And so this isn't just you can find a sequence which converges to A and f of xn converges to f of A. This is any such sequence xn converging to A, f of xn converges to f of A. So this is only saying something about what happens at the point A. The function could be continuous here and discontinuous elsewhere in the domain. So we say that f is continuous on some subset of the domain if it's continuous at every point. So at A for all A in the domain, all A in the subset. And then we say that f is continuous if it's continuous for every A in the domain. I'll take a seemingly trivial example, but this actually forms the basis of some important results. So if I take f of x to be constant, so it will be a function from the reals to the reals, and f of x is equal to c for all x. So c here is just some real number. So for a definition of continuity, assuming I want to show that it's continuous, I want to show that for any real number, so for any a in the reals, that the function is continuous at this a. And so that's to say that for any such real number and any sequence converging to a, we have that f of the sequence converges to f of a. Now this case is trivial because here I'm considering a new sequence generated from my original sequence. Now I don't necessarily know what that was, but I don't really need to. F of xn is equal to c, always, for the constant function. So that's a constant sequence. And so this converges to the constant value c, and this c necessarily is equal to f of a, again because f is a constant function. In a similar vein, slightly less trivial, but again part of the same idea, if I take the function no longer constant, but what you might call the identity function, so f of x is equal to x for all x in the reals. Let me just make sure that these are clearly separated. In this case we do the same thing. For any a real number, we take a sequence converging to a, so let a be real, xn converging to a, and then I consider the sequence f of xn. Well, f of xn is just equal to xn, and I know that xn is a sequence converging to a, so xn converges to a, so f of xn converges, well, f of xn is just xn, so that also converges to a, but this was the identity function, so this indeed was f of a. So in either case, these are continuous functions. So these are fairly simple, but they're made important by theorem, let me double check, 412. So these references are all coming from the notes. So quite simply, and this will be in shorthand, you can see the notes for more detail, but if I take two functions mapping from some domain, common domain, to the reals, some real number alpha, and f and g are continuous on the domain D, and then we have other functions which are continuous. So we have alpha times f is continuous, so a constant multiple of a continuous function is continuous. f plus g is continuous, sum of continuous functions, but of course because of this alpha over here, a linear combination of continuous functions is continuous, and the product. Although we do have a similar statement for composition, we have to be a little bit careful about domains. In this case, the product function, which I'll say a little bit more on, this is continuous as well. So these fall out directly from information that we have on sequences. So in particular, if I focus on fg, so if we have some a real number, we take xn a sequence which converges to a, then by continuity of f and g, we have that applying f to that sequence, an arbitrary sequence converging to a, this converges to f of a, and also g applied to that sequence converges to g of a. And so this is telling us together, using some previous knowledge on sequences, that if I just take the product term-wise, f of xn, g of xn, this is the product of two convergent sequences, or the product of terms of two convergent sequences, and so it converges to the product of the limits. So that's f of a times g of a. In particular, that's by theorem 2.2.4. So although on some level, talking about convergence of sequences, you'll have to talk about epsilons and n's, we can also use previous results to do a lot of that heavy lifting for us. In one outcome of this, using the previous examples, so we have constants are continuous and linear functions are continuous, or at least the identity function is continuous. We can find any product, so now we can get any power of x. We can find any constant multiple of a power of x as a result, and then we can find a sum of them. So for example, what we get from the two previous fairly trivial results combined with what is a fairly natural consequence of something we've seen before, we get that all polynomials are continuous. I'll go back up to the definition for a moment, because we will need this again. So it's important to point out that the definition doesn't really say very much about what the domain is. It just says that the domain is some subset of the real numbers. It's a real valued function. So in particular, we could consider a case such as the integers. So this is certainly a well-defined domain for a function. So we can consider functions such as functions from the integers to the reals. And all this is saying is a map from the integers to the reals. And any such function can be seen to be continuous. And so if we take xn, which is converging to some integer m, what we have to take into account is that all of the terms of the sequence are elements of the domain. And so we have all xn are elements of the integers. So just as an exercise, show that if you take a sequence of integers, which is convergent, so if you have a sequence xn converging to some integer m, so xn and indeed m are integers, then the sequence xn is eventually constant. What that means for us is if the sequence is eventually constant, then we're back in the same situation, although for a different reason, as we have in the first example. And so at that point, continuity becomes trivial. And so what you get from this, although please do go through the details, is that any function from the integers is continuous. The main theorem of the video will be to relate our definition of continuity, so this is the sequential definition, with what might be more familiar, it depends really what you've seen before, but with the epsilon delta condition for continuity. Which you call the definition is really a matter of preference. Ultimately, there's a theorem to say that these two conditions are equivalent, this sequential definition for any sequence and so on, and this epsilon delta condition. So this is to say that if you take any epsilon greater than 0, and just like we had for sequences, this is a value that's somehow given to you. You have to satisfy some condition based on any epsilon. So some epsilon is given as a challenge, you have to come up with some value. So we say that there exists a delta, and what you have control over is that x minus a is less than delta. So you can make x as close as you need to a, while keeping within the domain. And the condition is that you have to have the image of x within a certain distance of the image of a. So a graph is a nice way to visualize this. So if I take what looks like a cubic polynomial, but if I take some function and I take some point a, what this is to say that I have some value here, so that's the point a, f of a, and within some given epsilon, so I'm thinking of some epsilon that's plus or minus, so my epsilon is given, I want this f of x minus f of a to be less than epsilon. I want to be able to find some region, some little interval around a, which maps entirely between these two dashed lines. And so obviously if I take something quite large, so if I'm over here, I'm outside of that, but because this is a continuous function, I can always take a small enough region. So if I take a small region around here, and I map that up, then up to the quality of my graph, which of course no graph is perfect, but it will map entirely inside. Okay, but I want to say a few things about the proof. So I'll start with the case that f is continuous at some point a in the domain. And so this is to assume our definition over here. And in order to prove that for any epsilon greater than 0, that there exists a delta, in an application you might say, well, take epsilon greater than 0. So I'm imagining here I'm given a particular function, and then you go about to find some value of delta and verify this condition at the bottom. That's not really going to work in a general case, because finding some particular value of delta that works always for any given function is usually going to be a hopeless notion, and it's not going to be useful here. So in order to show that something exists, then what I'm actually going to take is the supposition. I'm going to assume that no such delta exists. So I take some epsilon greater than 0, which is now fixed. So I'm supposing this for this epsilon greater than 0. So suppose no delta greater than 0 exists, such that we have this condition. Now for this epsilon, we're supposing that no such delta exists. Now this is a cumbersome statement to deal with if you're not comfortable with these logical expressions. If you are, then negating it and working through it becomes relatively simple. But the way to think about it otherwise, okay, epsilon is fixed, we can more or less let that sit. If no delta exists, then this statement must break for every single delta greater than 0. So it must be the case that what we're saying here, x minus a is less than delta, implies that f of x minus f of a is less than epsilon. So that might be sometimes true, but this is a for all statement. And so in order for this to fail, it needs to fail at only one point. It may fail at many more, but it needs to fail only once. And so for any delta greater than 0, there exists x lying in the domain, which is within delta of a, and the condition that f of x minus f of a is less than epsilon is false, which can only mean that f of x minus f of a is greater than or equal to epsilon. And so keeping in mind our definition of continuity, we say that for any sequence converging to a, we know something about the sequence f of xn. It converges to f of a. This over here, that these are bounded away, so that these are always greater than or equal to my fixed epsilon, this is really going to break any convergence of f of x going towards f of a. It keeps things away. And so the idea here is that x minus a less than delta, these are getting smaller, it's getting close to a, and I can control that. I can generate a sequence xn which converges to a, but f of xn is always away from f of a, so it cannot converge. So in particular, this is any delta. If I take delta equal to 1 over n for some natural number, there exists xn such that xn minus a is less than 1 over n, my value of delta. And f of xn minus f of a is greater than or equal to epsilon. This line is really the key to the proof, because at this point we've set up a sequence xn which is going to converge to a. There's maybe some work to show that. I'll leave that as an exercise. So show that xn converges to a. And then we're in the situation of the definition. We have a sequence which converges to a, and we have to show also that f of xn does not converge to f of a. And this again, it should be relatively simple. We have that f of xn minus f of a is greater than or equal to this epsilon. So all we have to do is choose some other epsilon prime which is less than this, and we'll immediately get a contradiction to any claim that this converges. So this forces it not to converge to f of a. So with those, we have that side of the proof complete. Now I want to say something about the other direction, which is to assume the epsilon delta condition and to show that this original definition that we have follows. So we're assuming that for any epsilon greater than 0, you can always find a delta greater than 0, so that x minus a less than delta implies that f of x minus f of a is less than epsilon. In order to verify this definition follows from that, well, we ask, what does the definition say? So it tells us that any sequence converging to a, then f applied to the sequence converges to f of a. And so we take any such sequence. We take a sequence xn converging to a, and we want to show that f of xn converges to f of a. So we think about what does it mean for f of xn to converge to f of a. So in other words, there exists some natural number n such that n greater than or equal to n implies that the absolute value f of x n minus f of a is less than epsilon. And this already starts to connect up with the epsilon delta condition that we have here. So we have f of x minus f of a is less than epsilon, and we are assuming this condition. So as long as we can have, so it's x here rather than xn, but as long as we can have xn minus a less than delta, then this is going to follow. So the question is, how well can we control that? And the answer is very well, because xn converges to a. But since xn converges to a, so here the main difficulty is perhaps we think about epsilon as being this small quantity, but now we have delta greater than 0. So we know that there does exist some capital N, let me say n prime, such that n greater than or equal to n prime gives xn minus a less than delta. But in that case, xn minus a is less than delta, so we have indeed f of xn minus f of a is less than epsilon, so we're done. In the next video, I'll focus on examples using this to show that some particular functions are continuous at a particular point. So this almost becomes an algorithm, although there are points you need to be careful with. It's important to note that the abstract proof that we have of this result, or indeed of any result, often contain ideas that we don't see in just a direct application. So in particular, when we talk about examples, we will find a particular delta. In a proof, we go through some different steps. And so trying to understand the structure of the proof and the ideas used will help you to solve general abstract problems rather than focusing only on directly applying the definition and assuming the theorem. So both aspects are important for us.